Okay, here we are again. All right, so what remains to be done is we were partially through 5C. We started the method of substitution. Now, this is really one of the best strategies for solving for integrals. So we're going to spend a lot of time with it because it really can solve a lot of different situations. Not all of them, of course, but it really is an enormously useful tool for solving complicated integrals. And so we'll see it used quite frequently. And sometimes it's used in conjunction with other techniques, of course. But it gives us a way to take what appears to be an incalculable integral and turn it into something much more manageable. And so it works well under many circumstances. So we'll be focusing on that tonight. And then the part that is called 5D is basically more of the same, except that now we're introducing logarithmic and exponential integrals, and we also have some actual applications in here. Plus, towards the end here, we also will be looking at our old friends, the inverse trig functions like the arcsine and the arccosine and arctangent. They all get involved here too. All right, so this should be interesting. Now, I do want to make one announcement, which I will also formally post on the Moodle website, but next week, again, I'll be in the city. So instead of having our normally scheduled classes, instead I'll have recordings made available that will keep going and finish up what is left in the course, which, by the way, we are getting towards the end here. There's only one more chapter after this. There's only 6 chapters in this book. There's 6 very important chapters, but there's only 6. So when we're done tonight with chapter 5, here we have a question. Oh, the last day of class is, I think, the last day of July. I think that's what it is. If it's not, then it's the first day of August. But you think of it as, let's just say that we have 2 more weeks left. But we've got only one more chapter to go after tonight. So it's possible that we might finish a little early too. But if we do, you'll still have the same amount of time to hand in the final exam when we get to that point. So you don't have to worry about that. But I find that when I've done online classes in the past, for some reason, it always goes faster than it does in the classroom. I don't know exactly why, but so what I'm seeing here is that we're a bit ahead of ourselves here. We'll be done with chapter 5, most of it, almost all of it tonight. And that leaves 2 weeks to do chapter 6. I don't think that it's going to take that long. And we do have to review for the final, but in chapter 6. So we'll have to play that by ear a little bit. I really think we'll probably end up finishing sooner than the official last day of the class. So you might get a little bit of an early start on what's left of your summer vacation, but we'll see. Okay, anyway, let's get back to chapter 5C, what's left of it. And let's see, where are we? Okay, yes, the method of substitution. I was just saying how important this is for solving integrals. So the formal definition is here. Now, basically what they're telling us here is that this is something we should be using when a derivative requires the use of the chain rule. What we're effectively doing is reverse engineering the chain rule when we use the method of substitution. And so the strategy that we'll use is we'll use the letter u to represent some function of x in such a way that the derivative of u and u themselves can be used to replace the existing function so that we can use rules, simpler rules, to solve for our integral. So we did start to do a couple of examples here. Let's see, which one did we do? Oh, here we go. So imagine that we started with this. We have the integral of x squared plus 3 all raised to the 3rd power times 2x dx. Now, this one works out very well. It looks like a mess. And you could, in principle, multiply it out and create a very complicated polynomial, but it's not really necessary because we can do something a little different. Why don't we do this? Let's choose u to represent the value of x squared plus 3. And if that's the case, then du dx, the derivative of u with respect to x, would just be 2x, okay? Because remember, we're differentiating x squared plus 3, and the derivative of x squared is just 2x, the derivative of 3 is 0. And then that implies that du is equal to 2x dx. In other words, you just multiply both sides by dx. And so why are we doing all this? Because if you look at the original equation, it looks like a mess, and it is. But if you look at the substitution that we've made, all of a sudden we have something very simple. X squared plus 3 cubed is now replaced with u cubed. Okay, so if u was x squared plus 3, x squared plus 3 cubed is therefore u cubed. And of course, as you can see, but because of the choices that we made, du is 2x dx, which is right here and circled right here. So look how simple this new integral is. U cubed du. I think you'll agree that that's a much simpler problem to solve for than the original integral. And so we can apply the power rule, and look how nice that is. Oh, and by the way, just in case we forgot, the power rule, we see it all the time. The power rule for integrals tells us that if we have the integral of x to the n dx, let me just quickly remind us, whoops, the power rule for integrals says that if x, we have x to the n dx, this gives us x to the n plus 1 over n plus 1, providing n is not equal to 1. Then we have a separate, negative 1. Then we have a separate rule for that. But for every other case, x raised to any exponent except negative 1 results in x to the n plus 1. Oh, and don't forget the plus c. When we're doing indefinite integrals, we have to have that constant. Now, that means that here, the integral of u cubed is u to the 4th over 4, because n is 1, 3 rather. So here n plus 1 is 4 over 4. And now this is our result, but we're not really interested in the integral of u. What we really care about is the integral with respect to x. Luckily, though, all we have to do is take our choice of u, x squared plus 3, and plug it back into this formula. And you can see the final result is x squared plus 3 to the 4th over 4 plus c. So we've kind of danced around this problem. We made it into something simpler, which is much easier to integrate by changing the variables in the problem. Okay, and this is one of those clever type of strategies that you see employed throughout calculus from here to there. This is one case where our goal is to simply make the whole process simpler. By the way, whenever we do one of these problems, we can always go back and confirm that this is the correct answer. In fact, probably we should. Like here, for example, if f of x is x squared plus 3 to the 4th over 4, what we can do is rewrite this as a quarter of x squared plus 3 to the 4th. And now we're going to use the so-called chain rule, which means that, let's see, let me just add another slide here. So if you start out with some complicated function, this is what we're doing. Okay, so it's like the regular power rule. Remember when we had something like this? It's a similar idea, except that now, because the variable being raised to the n power is actually a function of x, so we need to take into account the derivative of g of x, and so that comes at the end, g prime of x. And so here, that's exactly what we've done. So in other words, I've got 1/4, and then when I differentiate this piece, I'll have 4x squared plus 3 to the third power times 2x, because 2x is the derivative of x squared plus 3. And so I end up with x squared plus 3 cubed, 2x, and that's exactly what we started out with. So we're able to take the integral, but we were also able to prove that we did this correctly. And they're all the same. The tricky part is to correctly identify the value of u. That's the challenge. What part of this should be u? And by the way, it doesn't always work. There are cases where the method of substitution will not speed things up at all. It will not give you a simpler result. And in those cases, you may want to try something different. But if it appears that you might be able to use the method of substitution, just be aware that if you make a bad choice for u, you'll discover pretty quickly that you're actually making the function even messier than what it started out as. So that's how you'll know you must have done something wrong. So here, what we can do is we can try letting this be u. Then du dx is 6x based on the power rule. And then du is 6x dx. Now, it just so happens that we have our 6x here and our dx here. So if we want to rewrite this, it's not really necessary. It's just when you're first starting out, you might want to do this just to make sure it's clear that you've done it correctly. So you end up with u to the fourth du. And of course, we've already seen that the power rule is easy to apply in a case like this. When we're done, we're going to wind up with u to the fifth over 5 plus c. And now all you have to do is replace the u with 3x squared plus 4, which we'll do in the next slide. So that's the same process we followed. So you've got the integral of u to the fourth du equals u to the fifth over 5 plus the constant. Don't forget that constant. And then here, all you're doing is you're replacing u with the value that we chose for it, 3x squared plus 4. And again, if you want to, you can take the derivative and you'll see that it is correct. All right, now here's another one. Now you notice many of these are very similar to each other. So, but don't worry, we'll have more complicated examples too, but I think this is something that we should get as much practice as possible. And you notice we're starting to see a pattern here. Often, I mean, the u itself is typically a relatively simple function, and it often does not have its own exponent. So you might think that u should be x cubed minus 3, but that doesn't do us any good because we will not have the information we need for du. But if we do it this way, u equals x cubed minus 3, then look how easy this becomes. Now, when you get to this point, you look at the integral and say, do I have this information or not? So here I do, even though it's slightly out of order. Oh yeah, very good. This is my du, this is u squared. And now all that remains is to make the substitution. And we're done. Okay, now here comes one that's not quite as obvious what we're supposed to do. So far, it's been pretty straightforward because we've had polynomials. And so that's usually nice to deal with, but let's take a look at this one. And, you know, when you first see it, you might say, oh my God, what are we supposed to do? But again, sometimes just a simple rearrangement of it can make it clear that there's a simpler way to approach this. So for example, let's look at this one. Ooh, that doesn't look too promising. Well, first things first, let's remind ourselves that this is equal to x in the numerator now. Does that do us any good? It might. So let's try this. Let's try u as x minus 1. It's just 1. Okay. Now, this one is a little trickier because if you plug everything directly in, you'll see that you actually have x over u to the 1/2 du. Now, you might say to yourself, oh, that is a problem, but look what we can do now. We need to get rid of that x. So how do we do it? Oh, wait a minute. If you add 1 to both sides here, that x can be replaced with u plus 1. Well, it still looks like a catastrophe, but no, maybe not. Let's see what we can do with this. Okay, so what we're going to do is rewrite this as actually there's yeah, I don't have anywhere near enough space for this. Hold on. Okay, well, it's a step forward. Now, keep in mind that u over u to the 1/2 is the same as u to the first over u to the 1/2, which is u to the 1 minus 1/2, which is u to the 1/2 power. So the first term is u to the 1/2 power du. Here, we simply have u to the minus 1/2 du. And now we can apply the power rule to both of these. Okay. So I've added 1 to the exponent and then divided by that same number. It's still a little messy, but we're getting closer. So you can see I've got all that here. This is where we left off right here. And then, of course, dividing by 3/2 is the same as multiplying by 2/3. And over here, divided by 1/2 is the same as multiplying by 2. So this is your final result, except for the substitution. Now, we go back, remind ourselves that u was defined as x minus 1. So now I just plug them in. And I'll end up with the correct result. And that's it, you're done. Wow, what a mess. But you can see there are a couple of bumps along the way. That was the clever part, though. When we get to this point where we had x over u to the 1/2 du, it must have appeared that we were stuck. We couldn't do anything. But then it turns out that with a little algebra, we can actually rearrange that x and write it in terms of u. And then we can go ahead and see if there are any rules that we can apply to this integral, but of course, even then we had to do a little bit of algebra on it to break it up into two terms where each one could have the power rule applied to it in order to get a result. Because even then, this by itself, this last part, is kind of a mess. But luckily, we were able to convert it into something not so messy and come up with the result that we were looking for. Now, here's an interesting set of problems. Sometimes when you try to use the method of substitution, you may find that you think you've found what you're looking for. You'll define u and du, and all of a sudden you discover that the expression you have is not exactly the same as what you came up with. In other words, you might be missing a constant, for example. Well, then there are ways that you can rearrange your expression algebraically to force it to work basically with the method of substitution. In other words, you should never give up with this thing. There's often clever ways of making it work. Okay, that's why it's so powerful, because it can be used with so many different cases. So now if you look at something like this, you might say, oh, well, we're in trouble now. So let's do this. So that would make du dx be 2x, and du is 2x dx. So you look at it and say, oh, wait a minute now. We're almost there. This is u to the 1/2. But this is not equal to du. But here's what we can do to get around this problem. Let's try this. Are we allowed to do this? Yes. Okay, so basically what you're doing is you're multiplying the outside of the integral by 1/2 and the inside by 2. The 2 and the 1/2, of course, cancel each other out. But what this accomplishes is that now you have u to the 1/2 du, and you're all set. You can use the power rule very easily. And then, of course, you have to rearrange it a little, and then you can substitute in u, and you're all set. So the trick was to say, oh, I need 2x dx for my du. I don't quite have that, but I'm only missing a constant. If that's all that's missing, I can supply it by multiplying and dividing by that constant. I haven't changed the results, and yet now I can go ahead and use the method of substitution, whereas before I couldn't have. So you end up with this is where we left off. And so in other words, remember, dividing by 3/2 is the same as multiplying by 2/3. So we would have had oh, wait a minute. No, I did something wrong. I know what I did wrong. You're dividing by 3/2 is the same as multiplying by 2/3. So you end up from here to here, you've got 1/3 u to the 3/2 plus c. And of course, remember, u was equal to x squared minus 5. And so that is your final result. Again, you can see it's like, you wouldn't think that it was, I mean, we're essentially manipulating the equation until we find something that's convenient. I mean, really, that's what we're doing. When it gets to the right point, to a certain point, then we suddenly have rules that we can apply to it. Wow, that was impressive. Now let's take a look at this one. Now, of course, right off the bat, your instinct is to say, well, you know what, based on what I've seen, let's try u here. Which means that du dx must be 3x squared. du is 3x squared dx. Now you can see there's a problem. We need 3x squared dx. We don't have it. But it's only missing a constant. And so because of that, we can just say, oh, no problem. So once again, I've multiplied the outside of the integral by 1/3, and in the interior, I've multiplied by 3. The two cancel each other out, so I've not affected anything. But look what I've got now. I've got u to the 9th du, which we know perfectly well can be, we can apply the power rule to that. And so let's see how that works. So we go through all the steps. This is the clever part. Okay, where you supply the 1/3 and the 3, and then we jump ahead and do some substitution. So this, as we saw before, is the same as 1/3 u to the 9th du. And of course, this equals, because of the power rule, u to the 10th over 10 plus c. We also have this 1/3 here, so we end up with u to the 10th over 30 plus c. And of course, once again, we have to replace the u with the original expression of x cubed plus 5, and that's it. How do you like that? Okay, so that was the end of 5C, I called it. Now we're ready for some more advanced, well, not so much advanced, but different applications of this. Let me just do one thing here before I forget. And while that's going on, we can open up 5D, which is the last part of chapter 5. If we finish this tonight, then we're completely done with chapter 5. And then all that remains is, like I said, chapter 6 and the review for the sample final. All right, I guess it doesn't want to, here it is. Okay, so here what we're going to do is our examples will now not all be polynomials. Yeah, I think I should have saved that PDF for later because it's gumming up the works now. Let's just give it a minute. Oh, I didn't even notice that. It refused to work. Oh my God, I've never seen that before. Huh. Well, all right, I'll just turn this thing off. I'll turn it in PDF later on. The only reason I need to bother with that is because if you're using a Mac, I'm creating these files on a PC. And if you have a Mac, what can happen is the equations, the symbols, and the handwriting can get mangled on a Mac. There's no guarantee you'll be able to see it clearly on the Mac. Sometimes it works, but sometimes it doesn't. So the only way I can really get around that problem is to put it into a PDF format, because with the PDF, what you're essentially doing is taking a picture of the slides, and then that way, no matter what computer you're using, you'll be able to see exactly what I'm doing. So, all right, so I'll leave that until later. So right now, let's get back to D. Anyway, so like I was saying, here we're going to be using the method of substitution but we're going to try different types of cases, and they won't always just be straight ahead polynomials. In particular, as you can see, we're going to go back and revisit our exponential functions and our logarithmic functions. So the rules for the e to the x are very simple. It's e to the x plus c. That's it. That's all there is to it. Now, if you have another base that, like instead of e to the x, you have some other constant, like a could be anything, 3, 7, it doesn't matter. Because it's not e, we need to incorporate the natural log of a. But other than that, it's the same procedure. Okay, so anything else raised to the x power when we integrate it will give us a result of a to the x over log a. Assuming, of course, that a is not 0, because if it were, the natural log would be undefined. So let's start with this one. Now, if you notice, it's not e to the x. It's so close. So here's what we're going to do. Because it doesn't precisely follow one of our rules, we can still use the method of substitution. And see, this is where practice is very helpful. You might wonder, what should we do about u? Well, it turns out the best choice is just letting it be the exponent. Because now it's negative dx. Now, of course, we don't have negative dx. What we can do is rewrite this as minus e to the minus x minus dx. See, now we're all set, because now we have e to the u du. And that turns into, as we saw a few seconds ago, the integral then is simply e to the x, or in this case, e to the u. And then, of course, we have to go back and replace the u with negative x. And that's it. We're done. Wow, that was interesting. But of course, the whole point of this is that the u was the exponent of e, not e itself. E, notice e is not included in the definition of u. Instead, what we're after was the exponent. And so all integrals involving e to the x will end up being solved in a similar way, unless, it's like multiplied by some other very complicated function. But just something like this, we'll always approach it the same way. So anyway, yes, so this is what we had. Well, with that under our belts, now we can try this one. And again, you're probably thinking, well, you know what, based on what we just saw, how about if we let u equal the exponent of e, du would therefore, du dx based on the power rule, minus 6x squared. So therefore we have du is minus 6x squared dx. Well, we don't seem to have that, do we? But guess what we can do? We're missing the minus 6, so let's try this. Minus 1/6 integral x squared e to the minus 2x cubed minus 1/6 dx. Well, you know what we have? If you combine these two, Oh, wait, sorry, I did. This is supposed to be the 6, -6. That's better. So in other words, if you consolidate these two, you can see yes, we do indeed have e to the u du. And then, of course, since u was chosen to be minus 2x cubed, that's it. It's all set. Okay, so I'll tell you what, this time let's prove it. We got our result and we want to prove that we did it correctly. And we can go to Symbolab too, but let's just go through the trouble of proving it. So we're claiming that this is the correct result, minus 1/6 e to the minus 2x cubed So keep in mind, the original function that we integrated was x squared okay, I lost it again, e to the minus 2x cubed. So if in order for this to be the correct integral, it must be true that when we differentiate it, it gives us back the integral. Now, here's one thing we need to remember. When you're differentiating e to some function of x, you're going to get e to the g of x times g prime of x. That's the chain rule applied to e to the x. So we're going to have minus 1/6. We'll factor that out. We'll start with e to the minus 2x cubed. And then here we'll have the derivative of the exponent. And of course, the c just drops out. These cancel each other out. Oh, yeah. Except that they're written, in the reverse order. We've just proven that our integration is correct. Okay, because we started with this function, we took the integral, we took the result, we differentiated it, and we proved that it equals the original integral. Therefore, we must have done it correctly. And that's always very satisfying. Now, the next one is going to appear to be quite a nightmare. And it is, but as you know, if you look at it hard enough, and again, if you try the wrong u, you can try something different. So let's look at this one. Now, this one is a product of some kind. Now, we don't have any rules just yet involving products. So we're going to try the method of substitution. Now, here's the hint. This complex expression is being raised to the 1/2 power. So if you notice how many times we've done this already, u is usually taken to be whatever it is that's whatever messy expression is being raised to an exponent. So in other words, why don't we try letting u equal 1 plus e to the x. And then let's see if we have the dx du that we need. All right, so remember the derivative of e to the x is just e to the x. So this means that du is e to the x dx. And we do seem to have what we're looking for. Okay, we can rewrite it a little. So we actually have radical u du, or u to the 1/2 power. And of course, based on the power rule, we have u to the 3/2 over 3/2, or 2/3 u to the 3/2. And of course, then we just need to plug in here 1 plus e to the x to the 2/3, and we're all set. So anyway, let me just scroll down here. It's typed out much more neatly. So here we had the u to the 3/2 over 3/2 plus c is 2/3 u to the 3/2. Then we substitute u, and we're all set. Okay. And again, we could prove it. We'll factor that out. Then we'll have 3/2 based on the general power rule. Which of course is the same thing as saying radical 1 plus e to the x times e to the x. And that's what we started from. That was the original integral. Yeah, there it is. So again, that means we did it correctly. Very nice. Okay, let's try another one. So again, we're probably wondering, what do we do about u? Well, let's try the messiest expression that's raised to an exponent and see if it works. If not, well, we'll try something else. Actually, I'll tell you what, let's, just for the fun of it, why don't we try the wrong thing on purpose? Suppose we decided, let's try u as e to the x. I mean, it's not impossible. Then du dx would be e to the x, and du would be e to the x dx. So you basically have that here, but then you don't have a u. What do we do here? This is 3u minus 2 squared, but that's not helping us because we don't have a rule for that. So instead, what we probably should do is try this. What if we just let u be this, all of this? Then du dx is 3e to the x and so what does that leave us with? Ooh, okay, now this is one of those cases where we don't quite have the du that we need. But we've dealt with this before. See, there's the problem right there. We need 3e to the dx, 3e to the x dx. We don't quite have it, but we're only missing a constant. So that means we can supply it ourselves by doing this. Okay, and again, so multiplied by 1/3 and by 3, it doesn't affect anything. And so all of this can be reduced to 1/3 of u squared du. Oh my God, it couldn't be much easier. Okay, so then we do a little more algebra. Let's jump down here and take a look at it. This is where we left off. So we end up with u cubed over 9 plus c, and now we simply have to replace the u, and we're all set. Oh my God. So after you've done enough of these, you start to realize, man, this is a very powerful technique, but sometimes you have to be a little clever with your choice of u. And also you have to have that model, never give up. It's not the case that you can always use this technique, but you can use it in a lot of cases. Oh my God, look at this one. That's looking pretty scary, but if you remember all the other ones we did, let's take a shot at u equals 1 minus x, which implies that du dx is negative 1. Du is negative dx. Do we have negative? No, but we can create it. So what we're left with is minus e to the u du. Now, because this is a definite integral, we are not going to need a constant. But what we do need is to evaluate it between 1 and 2. And remember how that works. Let's move this to the next slide. So you're basically doing this, replacing the u with 2. Oh, wait a minute. Before we do that, what am I doing? I have to replace the u with what we decided to call it. Otherwise, I'm going to get the wrong result. Oops. I was getting too far ahead of myself. Sorry. Instead, so let's try this again. So now we replace that u with 1 minus x. Now we're looking good. So we're going to have so if you notice what we're doing, in the book they would call this f of 2 minus f of 1. In other words, the antiderivative evaluated at 2 minus the antiderivative evaluated at 1. So in other words, in both cases, in the first case, x became 2, here it became 1. But remember, you're subtracting. And so here you'll have negative e to the minus 1 plus e to the 0. And that's it. You're done. Or if you want, you could rewrite it as 1 minus e to the minus 1. Or if you prefer, 1 minus 1 over e. Let me try that again. There we go. And that's it. So you've got the extra complication here that it's a definite integral, but the basic strategy hasn't changed. So you have to replace the u again with x, and then you can apply these limits of integration. Well, all right, let's try this one. So now I think we get the idea. We know already that we should probably try u equals 2x. Du dx is 2. Du is 2 dx. Do we have that? No, but we can supply it by doing this. So we multiply by half, multiply by 2, so we don't affect anything. We end up with 1/2. Definite integral from 0 to 2, e to the u du. So it's 1/2 e to the u. evaluated between 0 and 2. Now, because 1/2 is a constant, we can actually factor that out here. Okay, so this will be a very straightforward one to evaluate. So again, what I'm doing is I'm taking e to the 2x evaluated where x equals 2. Think of this as f of 2. And then this is f of 0. The antiderivative evaluated at 2 minus 0. Okay. Yeah, that's right. Okay. Now, this next one is actually an application, and it's kind of interesting because we're really doing the same thing, but this will give you a chance to see an actual real world setting where you could actually apply these techniques. The question is, how do you know which ones to use? So here's the story. We have bacteria, a colony of bacteria, and the growth rate, Q of T, is 3 to the T power. T is the time in hours. Q is the quantity of bacteria in thousands per hour. Now, 3 to the T is a very rapidly growing function. In fact, we went to Symbolab. Let's see. All right, I guess it's not open. Hold on. Yeah, you see what's happening here. Once it gets going, it's really growing very quickly. So what we're going to try to do is this. Given that we started with 10,000 bacteria, what function Q of T, the antiderivative, will give us the number of bacteria at any given time. So let's see if we can, let's go back and get this picture again. Hold on one second. We're looking for the total amount of bacteria. Well, first we're looking for the formula. So let me just grab this picture for a second. What's going to happen is that, oh, I forgot to paste it. The integral over a given range let's say this is 2. The total amount of bacteria is going to come from the integral over that range. Okay, so what we're going to do here is take this function and integrate it to come up with a function that will enable us to predict how many bacteria there will be at any given time. The integral itself is essentially measuring the rate of change. The QT is saying how many are there at any given time. So what we need to do is evaluate this integral, the integral of 3t dt, and then we have to show what the formula looks like, given that we started with 10,000 bacteria. So basically, this gives us an excuse to get rid of the constant, so to speak. In other words, normally right here, you have a constant, but because we're going to be given a given starting point, we won't need the constant, or at least we'll be able to solve for the constant. That's what I mean. So what do we do with something like this? 3 to the t, where have we seen something like that before? Oh, wait a minute. Could it be this one? So of course it's t's instead of x's, but you get the idea. Well, then it must be the case that we have 3 to the t over log 3 plus c. Okay, well, that's good. But what about this function? This c is not helping us. Okay, we want to figure out what the constant is. So this is q of t. The initial amount of bacteria. Oh, by the way, remember the bacteria is measured in thousands, so it'll actually be 10. You have to be careful with that. Initial means the time is 0. This is the current point in time. So in other words, what they're telling us there is that Q of 0 is 10. So if Q of t is 3 to the t over log 3 plus c, equals 10. All right, I got this written down here. It's a little bit neater. So let's jump down here. So this was the key to the whole thing. They're telling us that whatever this function is, it starts with 10 in the beginning. So that's saying that Q of 10, of 0 rather. And here, if you notice, we're replacing the t with 0. So just a little reminder, this was the original function. We're replacing the t with a 0, and we're setting this equal to 10 to 10. So therefore, this implies that the constant is 10 minus 1 over log 3. It's not a very pretty constant, but that's the constant. So that means that Q of t is 3 to the t power over log 3 plus this catastrophe, 10 minus 1 over log 3. And so if I need to know how many bacteria there are at any time, it doesn't matter if it's 2, 3, 5, 10, whatever, all I have to do is plug it in here. For example, Q of 5 would be 3 to the 5th log 3 plus that. Oh, whatever that is. Oh my God, hold on 1 second. I'll just get out the old calculator. Hold on, I'm having trouble finding my calculator. Oh, here we go. All right, so 3 to the 5th power. Hold on. Is 243. Divided by the log of 3. Oh. Oh my God. So we're looking at roughly 230.277 in 5 hours. That's how big the colony will be. It started with 10, and wow, look where it is after 5 hours. Here I've also solved for 2. If you wanted to know how many bacteria there are after 2 hours, you would do the same thing. And this time it's about 17. Oh, by the way, I almost forgot. This is actually 230,277 because remember the bacteria is in thousands. So here, after 2 months or 2 hours, it's about 17.282 or about 17,282. All right. So I don't know. That was kind of fun once in a while to see an application here. So, all right. So it's after 8. So I'll tell you what, we'll stop for a bit. And when we get back, we'll start looking at what appear to be terribly scary integrals. But in all these cases, we're going to see that there is a way that we can use the method of substitution as long as we choose our u carefully. And also possibly if we rearrange the expression algebraically into something more straightforward. Okay. So, all right, we'll stop here and we'll carry on when we get back. We'll see how it goes. All right, now we can try this scary looking one. But as I started to say before, right now we're thinking, what are we supposed to do with looking for you? But there might be a better way of doing this. Let's try this. Instead of leaving it like this, let's try to rewrite it. Well, let's see. Did that help? I'm not sure, but oh wait, I wrote the wrong thing. Sorry. This is not 1. This is x to the -1. Now there's 1 over x, of course, is x to the -1. So why don't we try this? Now, so far, every time we've used the exponential function, the u turned out to be its exponent. So let's try this. If u equals x to the -1, then du dx is minus x to the -2. It's okay. You can write it as -1x, but let's do minus x to the -2. And that means that du is minus x to the -2 dx. And so now all of a sudden it's starting to look more promising, isn't it? Because we're only, the only thing that's missing here is a negative. So what we can do is rewrite this as -1 to 2 e to the x to the -1 power. And then we'll have minus x to the -2 dx. And so all of a sudden, in spite of how scary it looked at first, this is just e to the u du. Ah, how do you like that? So we'll end up with e to the u evaluated from 1 to 2. And of course, now we have to replace the u with x to the -1. So that's what I've got here. So it's, yeah, this is where we just left off. So this becomes e to the minus e to the u evaluated from 1 to 2. And so what you're actually doing here is you are replacing the x with 2 here. And then over here, you've got 1. So it's minus e to the 2 minus 1 to the -1 power. Oh, you know what? There's a typo here. You know why? This should be minus a minus. I see that it's been corrected on the next slide, though. Because there's a negative already here, and you're subtracting a negative. So you're going to wind up with minus e to the +1/2 minus a minus e to the 1. And we'll end up with minus, let's see. Okay, that's better. So you can rewrite this if you want as e minus e to the 1/2, or if you just want to rewrite it with radical signs, you can write it as e to minus square root of e. All right, let me make a note of this. There's a small problem on slide 42. I left out one of the negatives. All right. All right. Oh, here's one. I don't want to spoil the surprise. Let's see. What should we do with this one? Well, I think we should try a similar strategy. Okay. In other words, let's rewrite it. 4e to the x to the -2 power. Of course, because this is in the denominator, it becomes x to the -3 power. So if we allow u to be the exponent of e, then du dx would be -2x to the -3. So we don't quite have that. But what we can do is now take this, and we're going to multiply and divide. We'll have -1/2 on the outside. On the inside, then we'll have negative 2x to the minus third power dx. So we do, in fact, end up with minus 1/2 e to the u du. Of course, and then we know how to solve for that. All right, so yes. Oh, wait, did I do something wrong? Oh, you know what? I just realized I forgot about the 4. There's a 4 here. So I have completely goofed it up. So in other words, the constant that we need is going to be different. Oh no. All right, I'll tell you what. Well, this is the good thing about handwriting. I can erase all this. I just realized I forgot about this 4 here. So we have to try this again. Yep. All right. So how did this work? So here, probably this would have been the smart thing to do. Just move it outside in the first place, this 4. So we don't have that problem. And then once we've done that, we can choose our u. So we'll choose the exponent of e. And just like before, u will be x to the minus 2. Du dx would be negative by the power rule. Minus 2x to the minus 3. Therefore, du is minus 2x to the minus 3 dx. And again, we don't actually have it set up that way, but it's close. But rather than multiplying and dividing, we're actually going to do something just a little bit different. Because of that 4 out there, remember, all right, let me just quickly remind you that u is e to x to the minus 2. Du dx is minus 2x cubed, and du is, of course, then minus 2x cubed dx. So we don't have the negative 2. We do have a 4 here, though. So here's the clever strategy. Take the 4 and rewrite it as minus 2 times minus 2. How does that help? Because look what we have now. So all of a sudden, there is a negative 2 in front of x cubed. So this now can be our du, and this is e to the u. So the constant was the challenge here. What do we do to come up with the constant that we need so that our integral contains du? Well, it was a little different from the other examples, that's for sure. So anyway, so we do have negative 2 e to the u du, which means we'll be evaluating this from 1 to 2 because this is a definite integral. And of course, don't forget u equals x to the minus 2. So now we'll evaluate this, replace this with a 2, and then we'll do the 1. Okay. All right, so here I've repeated that on the next slide, and now we can go ahead and do the substitution. So here, this was our x, it was replaced with a 2, and here's replaced with a 1. So you've got minus 2e. So remember, 2 to the minus 2 is 1/4. So that's what we have here. And then, of course, any 1 to any power is just 1. And that's it. We're done. Well, that was a bit of a mess. Excellent. All right. Well, now we can switch our attention to natural logs. All right. So just a quick reminder of some of the key properties. There's one here that we haven't seen before. We know already that 1 over x dx, the integral, is just log absolute x plus c. But there's actually 2 here that we haven't seen before. The integral of log x dx actually turns out to be x log x minus x plus c. And then if the log is a, we basically get the same thing, because here algebraically, this is the same thing as x log x minus 1. So these two are the same, except for this, which we've seen before. When we have a log other than natural log, we often have to adjust our results by the natural log of the base of that log. Okay, so some of these are surprisingly simple once you recognize or have seen these properties before. So for example, here, this one, we might say, well, what are we supposed to do with this one? Well, let's try this. Now, if you try 3, I mean, obviously du would be 0. So we're not going to try 3. So there isn't much else to choose from. Let's try x minus 10. Du is just dx. Oh, wait, sorry. Du dx is 1. And of course, that means that du is dx. So what do we have here? Let's try this. Let's put 3 on the outside. Now you recognize this one, because this means you have 3 log absolute u plus c and that's it. It was that simple. Okay, so this one right here, remember, when you have 1 over x dx, the integral is log absolute x. So here it would therefore be absolute log absolute c, but don't forget the 3. Wow, not bad. Oh, but one thing we do have to watch out for here is that this works for all x other than 10. Yeah, once in a while we run into a case like this. As long as x is not 10, this will be fine. All right, what about this one? Oh, what about this one? What are we supposed to do? Now, of course, there could be other options here, but let's just try u equals x plus 2. Because then du dx is 1 and du equals dx. So what do we have here? Oh, it couldn't be any easier. Wow. Huh. All right. Well, that's nice. Now, next, we're going to turn our attention to rational functions. Let's say we end up with something like this. Oh, no. What are we going to do now? All right. Well, let's try this. So now, because the second term has a higher order than the first term, it's probably worth our while to at least try letting u be x to the 4th plus 3x squared. If you try to go the other direction, if you tried u equals 2x cubed plus 3x, The problem with that is there's no way to find 6x squared plus 3 in this expression. So you're probably better off choosing, when you're not sure, pick the u that has the highest exponent and see if that works. And that we may have done the right thing here, because if you can see, du dx is 4x cubed plus 6x, and du is therefore 4x cubed plus 6x dx. Now, we don't actually have that, but we can get it because if you notice, this expression is 2 times this expression. So here's what we're going to do. So in other words, this is where we just left off. And this would be oh, I see what I did. Okay, yes. So then on the next slide, you can see, so given that this is u, this is actually, since du equals 4x cubed plus 6x dx, we could say that this expression you could rewrite that as 1/2 of du. And so if you do that, you've actually got 1/2 u to the -1 du, or and of course that just means that we're going to have a logarithm. Okay, so in other words, when you have something like this, and that's exactly what we have here, except that it's u. 1/2 du over u means we have this, and then of course now that u, the integral of 1 over u du, is the log of u, absolute value of u, and now we make the replacement of u. Remember, u equals x to the 4th plus 3x squared. So this ultimately, the bottom line is this is the final answer. So here the clever strategy was to say, well, you know, we're getting close to having this du, but it's not quite there. And yet it's a constant that's the problem. So why don't we rewrite this as 1/2 du and then move that 1/2 on the outside, and then we'll be all set. And then the rest falls right into place. Okay. Now this next one requires one of those rules involving logs that are not natural logs. In fact, let me go grab the one we need. Here we go. Just as a reference. So here a is, of course, 2. So really there isn't anything to do except follow the rule, because you can see it follows exactly along with what you see up here. So you'll end up with x over log 2 times log x minus 1. Wow, that was easy. Once in a while, it turns out to be pretty straightforward. Not always, of course. Now, unfortunately, we can't completely avoid trigonometry in these examples. So now this is an intriguing case because it's hard to tell just by looking at this whether u should be sine x or maybe it should be 1 plus cosine x. Well, all right, let's try this. So which one of these, even though neither one of these is in the equation, I would say it would be easier to introduce this into the equation because all we need is a couple of negatives. By putting them there, the numerator, all of this is in fact du, and this is u. So this is natural log of u evaluated from 0 to pi over 2, or we can rewrite that as the natural log of 1 plus cosine x from 0 to pi over 2. So you've got log actually, this is an absolute value. Let's not forget that. Okay, so in other words, you notice how the x's have been replaced first with pi over 2 and then with 0. And so that when you're done with all that, it turns out that this is 0. And the cosine of 0 is 1. So it reduces to something very simple. It's the log of 1 plus 0 minus the log of 1 plus 1, as you can see here. So it ultimately ends up being the log of 1 minus the log of 2. Now, the log of 1 is just 0. The log of any base of 1 is always 0 because 0 to the first power, a to the 0 power is 1. So you end up with 0 minus log 2. So, that should have been negative. I'll fix both of these and post the corrected solutions later on. Okay, yeah, that's definitely a negative. Now, here's where our old friend, the inverse trig functions come into play. The arc sine, the arc cosine, the arc tangent, and all the rest. What happens is certain integrals, there's a form that you start to recognize after a while. And so, in other words, if you look at this first one, for any constant a, if your integral is du over a squared minus u squared, then the integral of that is the arc sine of u over absolute a, plus the constant, of course. If the denominator is a squared plus u squared, that works out to be 1 over a times the arc tangent of u over a plus c. And then finally, in this last case, the last one involves the arc secant. And by the way, how will you know these? Well, after a while, you start to recognize them. It's just one of those things where you just have to get some practice with it. And you might say, well, how should I know that this is an arc sine or cosine? Just practice. It's just that simple. you might have a case that looks similar to this, but not quite the same, and it won't be an arc sine or a cosine. But anyway, this last one, u radical u squared minus a squared, you can see that this is 1 over absolute a, arc secant u over absolute a plus c. So let's look at a case like this. Now, it looks kind of familiar. Let's see if it falls into one of these categories. Like, for example, maybe it's this one. If a is 1 and u is x, then we're all set. Because look what we'll have. And of course, you can see from up above, that's the arc sine of u over absolute a. And we're going to evaluate that from 0 to 1/2. And of course, a is just 1. So you just have the arc sine of x evaluated between 0 and 1/2. Okay, so the 1 is a, so it basically drops out. The u is x. So you basically just wind up with the arc sine of x evaluated from 0 to 1/2. And it turns out that the arc sine of 1/2 is pi over 6. The arc sine of 0 is 0. So the final result is pi over 6. Now, if you didn't recognize that this is an arc sine formula, well, I don't know, like no matter what you try for u, you can see you're not going to get anywhere. So that would be a hint that you're supposed to try something different. Okay, in other words, if you can't find a proper u, then you may be looking at a completely different category, like here, the fact that this is an arc sine. So that's when you want to look and see if there's any other techniques you might overlook. Now look at this one. Does it look familiar? Yes. Well, it looks very familiar because it looks like this one. As long as you recognize that a is 2, u is 3x, and du is 3x dx. Now, here we don't have that. We'll need to supply. Oh, wait, sorry, hold on. U is 3x, du dx is 3. So du is just 3 dx. Okay, so we're only missing a constant. We'll put that here and here. And then we'll have du over well, I can write it as a squared. And so that means I have 1/3. This one does need a constant. U is 3x. This is 2. Now, I mean, you can see there's an absolute value. We don't really need the absolute value because 2 is clearly a positive number. Oh, and that seems to be it. Wow. Yeah, that's it. We're done. Because we recognize that this is in the same form as this, even though we needed to supply that 3 for ourselves, we know how to do that. We had plenty of experience tonight doing that. And so you can see that we end up with 1/3 times the arc sine of -1. The arc sine of 3 u over absolute A, which is this. Now, this one is a little different because you can see there's no square root and there's no subtraction. And yet, you also recognize that u substitution doesn't look very promising. So you go back and see if there's any of these formulas that might apply here. And you scroll up and say, oh, wait a minute, this one looks good. Possibly this is it. Let's compare them. Oh boy, that seems to be the right one. So again, A is 1 and U is 2x. So we don't have the 2. We can create it for ourselves. Well, that means we're going to end up with an arctangent. So 1/2, there's 2 dx. And so let me just copy the formula again. Okay, so remember A is 1. And U is 2x. All right, so here's the A again, here's the U, and that's it. Now there's others too, but I mean, those are the more down to earth ones. There's some really messy ones, but we're not going to deal with those right now. So anyway, that was pretty much it for chapter 5. There might be a few more applications, but we've covered everything we needed to cover here. So what remains to be done is 6. And 6 is, the title of the chapter is Applications of Integration, although I must say that it's not what it sounds like, because yes, there are some applications, but they're actually introducing several new techniques. So I'm not so sure if that was the best title for that chapter 6. Think of it as an extension of what we've been doing. They'll be introducing some new ways of applying integration to a few new cases, including the hyperbolic trigonometric functions, which we haven't thought about in a long time. And there's a couple of others where they're showing you how you could use it to calculate areas and volumes. So if you had some kind of physics application, then this would be very well suited for it. In fact, Newton basically invented calculus in order to describe the laws of physics as well as the laws of motion that he, as we know, he created. The 3 laws of motion are his, because he was, of course, an astronomer, among other things. So physics is a very natural application of this material, but so we'll do some of that, but the focus will be more on the new techniques. And so we're getting towards the end, basically. It's like we're in the Greek marathon. Remember, it was not 26 miles, but it was 26 miles and some yards at the end. We're getting towards those yards right now. So we're done here. And so when we're done with 6, we'll have a sample final. And then the real final will be in the last 3 chapters, 4, 5, and 6. And then we'll be done. So like I was saying before, there's a very real chance it will be done earlier than the official ending of the class. But no matter when we actually finish, you'll have plenty of time to finish the exam. And so that's not going to be a problem. But we may not have to have quite as many sessions as we originally thought. Mainly, like I said, because somehow this just goes faster on the internet than it does in the classroom. And I don't know why, but it just seems to work that way. So we're getting towards the end. So for now, all you have to do is basically make sure you understand what we've done. And then remember, next week, everything will be recorded. So when the recordings come out, just watch them. And then at some point, we'll start working on the sample final. And then, I'll post the real final, and then we'll be done. All right. So I guess that will be it for tonight. And I'll see you all soon. You're welcome. And good night, everyone.
Thank you.
Okay, bye.